So thank you for the introduction and thank you for inviting me. I wish I would have seen Martin's slides before because I was somewhat nervous because I'm supposed to speak at a memory management conference with a computer architecture background, so I was kind of worried, but I would have been less worried if I had seen Martin's slides. But having said that, again, thank you for inviting me, and I'm not organizing the conference, but I guess since I am based in Korea, I would like to welcome everyone to Korea. I don't know if you noticed, but the weather is going to turn really bad sometime real soon because the rainy season is starting soon, so hopefully you'll miss that before you go back home. Now, as you probably know, the conference is being held in Seoul, and I sort of sarcastically tell foreigners that, again, Seoul is a metropolitan city, right? It's like New York, any other cities you've been to. But if you drive about an hour out, you'll really hit the countryside. So you'll see the rice paddies and so forth. And I joke that right behind the rice paddy, you're going to see a DRAM paddy. And they're going to make all sorts of DRAMs out there. Why do I say that? I don't have a strong background in memory, even from an architecture perspective. But having been in Korea for 15 years, I sort of feel like I know a lot about memory. Having worked with the industry folks, you sort of, by osmosis or something, you just sort of have a feel for knowledge of different aspects of memory. And for the next 30, 40 minutes, I'm going to try to act like an expert in memory. So we'll try to do that. And come from it from a different perspective than most of you probably come from. So I come from more of an architecture, more of a technology perspective. So hopefully I'll give you a different perspective to think about. Now, for a talk like this, I really don't like to summarize papers and give you summaries. I think you guys are all smart enough to read papers. So I'm hoping to give you at least a few things to think about or chew on, especially given that a lot of you probably come from different background as well. So recently I've done some work in PIM. So I originally titled this PIM memory management, but again, that sounded a bit too boring. So for the past couple of days when I was trying to update the slides, prepare the talk, and I sort of tried to change it to domain-specific memory management. I still don't know what that means, but it sounded cool. So I sort of came up with that name, but I'll try to explain where I'm coming from. Now, I'm not going to have any fancy slides about AIs and all the importance of transformers and so forth, but I'm going to start with a very traditional computer architecture slide. If you've taken a computer architecture class, you've probably seen this. We live in an era of domain-specific architecture, right? We're designing chips to be more specific, and you see these sort of scope of different type of architectures out there. So you have CPU on one side that provides you with the highest flexibility, and on the other end, you have ASICs, or domain-specific architectures that provide you with the least amount of flexibility, but the highest amount of performance. Again, your NPU, TPU, various different accelerators would fall under this, and then you have GPUs, FPGAs in the middle, right? Again, I don't think this is anything new, but again, this is where people refer to as domain-specific architectures. You're designing architectures for a particular domain. So having said that, again, this is for the processing side. Now, another thing you've probably learned in computer architecture is that there are three aspects of computer architectures, right? There's the compute part, the one where you actually operate on the data. Then there's the memory where you're storing the data for use at a later time. And then there's a third component, which moves the data between the various different components on chip, off chip, and so forth. My area of expertise, or where I focused on, is the third aspect on the bottom, the communication. So that's where my expertise lies. But recently I've worked in the other aspects, and I'll try to touch upon how these sort of impact sort of the memory architecture, memory design. But since, again, my focus has been on the communication, I just wanted to share this one particular slide where I would argue that networks today are also falling under this realm of domain-specific architecture, right? You have different types of networks out there. And again, domain-specific networks is something that we just put together as a terminology for one of our papers. But you have general-purpose networks, think Ethernet. And then you have networks that are designed specifically for particular systems. For example, Google TPU has their own custom interconnect that's designed specifically for their systems. It's obviously not flexible. It's not going to work on your CPUs, but it gets the job done in terms of their particular systems. So that's where I'm coming from, and I'll briefly touch upon this later on when I talk about some aspects of PIM. But again, I don't think I need to tell people here what PIM is, right? Again, it's this notion of you moving the processing to the data, different granularities of PIMs and so forth. So again, I sort of try to, in a cartoon, highlight different types of PIMs that are out there. But again, I don't think that's really important for this particular talk. But one aspect that is that I'm sure you've heard that PIM is not a new type of an architecture. If you go back to the 60s, 70s, that's when the first sort of notion of PIM came out, when people were suggesting you put compute inside the memory. Now, those similar ideas were revisited about 20 years later. This was in the mid-90s. But surprisingly enough, PIM has sort of re-emerged 20 years later. And now this time, I think it's a lot more serious, right? You have memory vendors actually building PIM products and different companies sort of trying out PIM architectures. So the question is, well, what is different today than 20 years ago? I think one can argue is this sort of the domain-specific aspect of it. I think there are key architectures, key applications that are requiring particular performances, bandwidths from the memory systems. And that's where I think you're seeing a lot more interest in this sort of what people call PIM, what I'm going to refer to here as domain-specific memory. So if you look at the actual publication, that presentation from Hynix a couple of years ago on their PIM architecture, they actually use that word domain-specific memory. So they used all the buzzwords, I think, in their title, memory-centric computing, and this notion of domain-specific memory. It's domain-specific memory because their memory architecture is good for just one thing, which is just sort of a GenV sort of an operation. That's it. But again, it excels at that particular operation, so it's something that's worthwhile. So given this notion of domain-specific memory, and if you go back to the first slide of domain-specific architecture, I think you can actually draw a domain-specific memory sort of a spectrum. So again, this is something that I sort of drew together, put together myself, so I'm not sure how valid this is, but on one end, you have sort of the general purpose memory, right? You have your GDDR HBMs. And on the left four is actually different types of PIMs that have been proposed, and I've purposely laid them out in this particular order because they provided various different trade-offs in terms of programmability versus efficiency. For example, the Hynix PIM on the right is very dedicated in terms of functional units and has no programmability. On the other hand, ISMM', which is a type of a PIM that has been proposed, actually has a programmable core with a 14-stage pipeline. And then you have the Samsung PIMs in the middle, which provides some amount of programmability, a lot more than what the Hynix provides, but it's not as flexible as a general purpose core. So again, that's sort of the spectrum of what you have in terms of different types of memory. Now, while I was preparing for this, I obviously went to last year's conference and looked at the proceedings and the keynote. And the keynote last year was actually someone that actually knows about memory, someone that knows about PIM, a speaker from SK Hynix who talked about the details of their PIM architecture. So fortunately, I'm not going to go into the details of what the PIM architectures look like. I highly encourage you to sort of look at it because he provides a very good overview of what the architecture does, what they use the PIM for, and so forth. But having said that, again, I was sort of watching through the video, and it was very hard not to notice the last slide. The speaker throws out various different issues in terms of the challenges that they face in terms of PIM. So again, you see the memory hierarchy, where do you place the data, sort of the traditional questions that you see. Now, while I was sort of staring at this, I couldn't help recall a session that I attended about 6 years ago. This was a conference called DAC, so it's a design automation, but deals with computer architecture aspects as well. There was a speaker from AMD that we invited for a special session, and he talked about sort of data placement, NUMA awareness across the entire system hierarchy. And if you sort of stare at these two slides, they're actually very similar. Well, I guess you have to turn them upside down, sort of. But in terms of the issues that's being addressed, it's very similar. So the question is, well, what is different today and what has changed, or maybe what has not changed, right? I think over the past 6, 7 years, what you can argue is that the technology has advanced significantly. But in terms of how we manage the technology or the architectures, maybe we haven't advanced as much. So I think that's maybe something to think about, given that these sort of two presentations were made about 6 years, 7 years apart. Having said that, here's sort of the outline for the rest of my talk. I've talked about sort of giving you an introduction into domain-specific architectures memory. I'll talk a little bit more about PIM architecture challenges and the way I would like to view PIM, which is in terms of PIM as a memory and the sort of the common terminology that everyone here knows, which is locality. I'll introduce a little bit about sort of some of the work that we've done in terms of domain-specific memory management, in terms of how you use that, how it's needed for different types of architectures, and wrap up with a few summary challenges. Now again, given that this is a talk about PIM, I'm just going to give you a quick tutorial, 1-minute tutorial in terms of what PIM architectures look like. And again, because of the fact that M.Eng is publicly available and many of us use it for research, I'm going to talk about that because we've also published papers with this. So again, if you look at a traditional host, it has its regular DIMMs on the bottom. And on the top, it has a separate dedicated PIM, PIM-enabled DIMMs from M.Eng. And if you look at it carefully, it's organized hierarchically. So you have within a DIMM, you have 2 ranks, and each rank with 8 chips. And within 8 chips, you're going to have 8 banks. And now, up till at this point in time, the organization is very similar to any sort of memory. Now, the key difference here is that within each bank, it has its local memory. In this particular case, it's shown here as an MRAM with 64 megabytes. But you'll also notice there's what's called a DPU, which is a data processing unit, or DRAM processing unit, which is for the actual computation itself. And then you have a scratch pad memory called the WRAM. So this is a architecture that was proposed, again, by a French company. And many researchers actually use this because of the flexibility it provides, and it's readily accessible. And again, we've published paper using this system as well. But having said that, I think it's really worthwhile to look at where does PIM stand today. Again, I think that this was proposed about 5, 6 years ago, and various different PIM systems have come out. With all due apologies to the second speaker, who's going to be talking about a garbage collection based upon an M.Eng system. I don't know if the speaker notices, but M.Eng has closed down. This is, if you go to their website, this is what you'll see, and you can't get access to any of the links. So again, I don't know the internal details, but I believe this was announced within the past 2 weeks or so. So this is very recent. There's another company that was doing sort of PIM-related, more in terms of SRAM type of architecture, called Untethered AI. And you'll notice they haven't done too well. This is also announced within the past couple of weeks as well. So again, I guess timing is everything. It wasn't too great for preparing for this particular talk. But having said that, I thought I would have some fun with this. We all use ChatGPT, and given the state, I asked ChatGPT to write a eulogy for me. And this is what it had. This is really fascinating. Again, all of you have used this ChatGPT before. The only thing I edited is the highlight, because that's the part I wanted to read. Surprisingly, the bold part is something that ChatGPT thought was worthwhile. So again, it talks about that dare to ask, what if your RAM had opinions? Actually, I'm not a native English speaker, so I couldn't figure that out, so I had to follow up and ask them. And so for those that are not aware, it means if you have an opinion, you're thinking. And that's what the sort of the sarcastic joke here is, that they were trying to get the RAM to think, which is what the PIM is effectively. And then it talks about how M.Eng promised to transfer data-heavier workloads and perhaps confuse a few system integrators along the way. Again, I asked it on purpose to write something sarcastically, but I think it was really on the point. And the last line here is really interesting. Like many brilliant ideas in computing, M.Eng hit the silicon ceiling known as the industry of adoption. Again, I don't think that's a common word we use, but that's what it said. Here is the part I think that we should all be sort of aware of. While they built it, and again, this is perhaps the only PIM that academics can actually use. The industry mostly shrugged. turning out people to rewrite their software stack, compiler tools, and mental models was maybe a bit much, right? And it talks about you were ahead of your time, slightly to the side of the market, and you have to, again, apologies to the second speaker, it may be gone from the lab, but you live in the 43 PowerPoint decks and a dozen PhD dissertations. Again, I don't mean to be rude. I was just trying to have some fun with it, and I think that ChatGPT did its job writing a sarcastic eulogy. But it does point out some of the key aspects here, right? It's a cool tool. It's a cool toy, right? But that does not mean it's going to be widely adopted by the industry. So the question that I asked myself, again, I have very limited PIM knowledge. Again, I've never designed a DRAM in my life, but again, I've done some work with PIM, and I've done some work with computer architecture in general. And I think if you leave this talk with anything, I would suggest you sort of think about this particular question. Again, you all know what a PIM is. PIM is the processing in memory. You're bringing compute to the memory. Now, when you bring a compute, again, you accelerate something into the memory. Now, what you have, is that an accelerator or is that a memory? Right? I think that's sort of a fundamental question that needs to be answered, and maybe that has been a problem, right? So I've drawn some cartoons here on the bottom that sort of tries to illustrate it, but here's sort of another interesting story. So when we first started working with this ISMM architecture, obviously, as a professor, what do? You tell the students, go learn about this and tell me about it, right? And they started learning how to program it. And again, ISMM had this entire software stack where you could actually run code on it. But after about a few weeks, after the students sort of got used to programming the ISMM PIM architecture, he comes back to me and says, this feels a lot like CUDA. Right? Which was sort of a surprising statement, but he was, I think, right on, in the sense that the way we've treated the PIM architecture is as like a GPU, as an accelerator, right? And again, it's great because it gives you all this sort of compute and it gives you this increased amount of memory bandwidth, which is all great. But is that really going to sell? Again, I'm talking more from a sort of a business perspective. Again, I'm not coming from the industry, but I think this is something that needs to be considered. You're taking up real estate when you're plugging in these devices, right? You're actually taking away real estate for memory capacity. I think this is a well-known issue, but Samsung had an HBM stack with PIM implemented on top, which is great. It did a lot of it had a lot of cool features, but it ripped out about a third of the memory capacity per layer. Now, given that one of the biggest challenges of HBM is memory capacity to begin with, right? This is not something that's going to fly with a lot of the customers, right? So the fact that you're putting these sort of expensive accelerators, well, does that really make sense, right? And again, this is my own personal opinion. There's been a lot of great research in terms of PIM over the past 5 years within our community in terms of computer architectures. However, I would argue that all of these work treated PIM as an accelerator. Now, again, if you have an accelerator, if you're talking about a TPU or NPU and all these sort of things, they view that as an accelerator. But when you're trying to touch upon a PIM architecture, well, is that really an accelerator that you would want if you want to accelerate something? Or would you really rather go to a sort of a TPU-like architecture? If you really wanted something like this, I would argue that you want to consider this more as a processing unit or as a memory unit. Right? So that's sort of the question that I sort of pose to people here to think about. Right? Again, if you're expecting an answer from me, I don't have the answer, but I'll share you my opinion is that PIM really needs to be viewed as a memory. It's a memory that can do functionalities. It can do computation near memory. But if it's viewed as primarily as an accelerator, that's a lot of wasted memory. And I don't think, given the importance of memory bandwidth and memory capacity for a lot of these workloads today, you're not going to see a lot of customers too happy with that. Again, a lot of this is just my opinion based upon some of the work that we've done. But again, PIM should not be viewed as here as an accelerator. Again, this makes for cool research. And you can argue that you have about 1,000x improvement versus alternatives. That's great. But in order for PIM to be a much more viable technology, I would argue that it has to become more viewed as a memory. And I'll talk a little bit more about what I mean by that. So I'll try to dive into some of the work that we've done in terms of looking at how we should view memory sort of organizations, including PIM. Now, I'm going to go back about 10, 15 years ago when we did some work with a new memory technology back then. It was called what's called a hybrid memory cube. So it was a 3-stacked memory with high-speed IOs, high-speed SerDes that allowed you to sort of daisy chain these together as well as connect to various different hosts as well. Again, this was a cool technology that lived for maybe a few years, just long enough for this particular student to graduate, I think. But it was an interesting technology back then. Now, what it enabled is that systems back then were built in this sort of a fashion. You have CPUs host with its own memory and then a network. This is what we refer to as sort of a processor-centric. Now, given that the fact that these memory modules have networking capability or IOs, SerDes, you can actually connect them together and form something what's called a memory-centric organization. So what we did was, again, we proposed various different systems back then. This was a multi-GPU system back then. You could have a system where you have multiple memories, multiple memory interfaces. You have links connecting the GPUs and then BCIs together, right? But can we do something better with this because of the fact that you have so many interfaces? And this is what we proposed back then. We proposed this notion of what we call the unified memory system, where you have essentially memory pools sitting in the middle, right? So you're viewing the entire memory as one sort of blob of memory, which is shared by the various different hosts. And we refer to this as sort of what we've called a memory-centric organization. Now, having said that, I think technology has changed such that this sort of architecture is being revisited with this notion of CXL and so forth. Why do I bring this back? Sorry, I'm going to skip this just for lack of time here. I'm going to try to tie this into how we should view PIM as well. So this was a work that we did where we were trying to accelerate LLMs inference. And if you look at the details of how the workload itself, you're going to have compute-heavy work components, which is effectively matrix multiplications. And then you have memory-intensive workload kernels, which is matrix vector multiplications. Now, domain-specific architectures such as the systolic arrays or TPUs are great for the matrix or the compute-intensive. And then you have the PIM for the memory-intensive kernels. So given the trade-offs there, well, wouldn't it be the best of both worlds if we could combine the two, right? So that's the work we did. And when we did this, it was done in collaboration with Hynix, which had their own PIM architecture. And then there was a startup and company, which was purchased, bought out, that had their own NPU. So we were combining this. Again, you have the cost-efficient architecture for the compute part, and then the PIM for the memory-intensive part. So the first architecture we could come up with is something like this, where you have the host, in this case the NPU, it's connected to the PIM, but the host, in this case the NPU itself, also needs its own memory. So that's sort of what we call the partition or the dedicated memory sort of an approach. Again, this is great because you could let the PIM run in parallel. You could let it do its compute while the NPU does its job while accessing its own memory. Right? So it's the good thing about this part is that you could maximize parallelism. But you notice you have your standard DRAM, again, which is the memory for the NPU, but the PIM itself is also memory. You're essentially throwing out half the memory to use the PIM as an accelerator. Now, the other thing about these workloads, again, for the models that we use, there's quite a bit of sharing of the data. So again, I encourage you to read the paper itself, which was published in ASPLOS last year. Depending upon the models you use, you have quite a bit of memory data that is shared. What does that mean? You have quite a bit of data movement between the PIM to the NPU to the standard DRAM and back and forth, which is really not the most efficient usage. So that's not only bandwidth over it, but there's, again, significant impact on the the memory capacity itself. So the proposal here was, we called the IANIS, which was standard for integrated accelerator, which was to combine this notion of PIM and the MPU together, right? So this is what was proposed as part of this work. Again, where you have sort of the PIM and sort of the host memory sitting together on top of each other. So again, we've drawn this sort of in this sort of a cartoon fashion, but what this really means is that the memory of the PIM is used for not only the accelerator, the compute part, but also for the memory for the MPU itself, right? So you don't have to copy the data over, and obviously you get better usage of the memory capacity as well. And if you're really counting, all of the DIMMs now could support PIM, so you actually get more throughput or flops as well. Did I do that? So again, we called it IANIS because it was an acronym, but it still represents a God that had two faces. So it's sort of an analogy to the fact that the memory PIM device could serve as both a memory and an accelerator. But we did not have to have a partition sort of a system, right? A partition memory organization, but we were able to have a unified sort of an organization. Now again, I'm skipping through all the details of the papers itself, and you can find all the results and the details there. But what we were able to propose is, again, a domain-specific PIM plugged into a domain-specific architecture to effectively create a domain-specific system. But again, just plugging that in and using that obviously has its challenges. So we had to come up with new ways of scheduling. We ended up calling it PIM access scheduling, because if you look at any sort of CPUs, GPUs, you'd have what's called a memory access scheduling for the commands going out to the memory itself. On top of that, you have to also schedule the operations on the PIMs itself. So that's sort of the changes that's required for the PIM itself, or in terms of the memory management. So again, that's how we should be viewing PIM itself. But again, if you talk about memory management, if you talk about memory hierarchy, it's really hard to not talk about locality, right? Again, I think that's the first thing you learn. But surprisingly, that word has been missing in PIM. You never hear this notion of PIM locality. What do I mean by that? Again, I've shown here various different PIM architectures that have been built, and you have different units of granularity, but I'm going to call it a node here, which is the granularity of memory and the compute. Now, if you look at HBM PIM, it has 16 megabytes, 32, 64 megabytes, and so forth. What that means is that the compute can only access its local memory. What that, again, means is that if you're trying to access data that's on a different neighboring bank, then you have no way of accessing that. Actually, you do have a way of accessing that. You just have to go back to the host. So obviously, that introduces a significant amount of overhead. So you don't have the ability to do this. I try to avoid having plots, but I guess I have one here. We've run this experiment on ISMM system where we looked at a couple of workloads. The details of the workloads are not really important, but you'll notice for any sort of scalability plot, you want something linear. And we do get that for these sort of kernels if we're just looking at the compute part, right? But if we look at the overall performance of these two workloads, again, these were just two that I'm just showing here, it's not going to be the case. So the question is, why is that the case? It all comes down to, I would say, data movement, right? You have to move data between the PIMs. You have to do communication. But again, most of these architectures, PIM architectures, do not support that. So here's sort of a simple cartoon that sort of illustrates the problem that we're talking about, right? So you have the communication first, where you take the data from the regular DIMM and you actually have to copy it over to the PIM itself. And then you're able to do the work on your local data. And again, as long as you're working on local data, that's fine. You're going to get great throughput in terms of compute as well as high memory bandwidth, right? But at some point, if you need to access data from a neighboring DPU, right, there's no way of actually grabbing the data from the neighboring, and there's this notion of what I refer to as sort of PIM locality. You only have access to your memory bank, which in many cases is 32 or 64 megabytes. Again, obviously for some workloads that's sufficient, but for others that's not. Especially if you have to do, let's say, a collective communication between the different compute units. So again, modern PIM systems actually do support communication, but again, it has to go through the host and then has to come back and be copied back over. And then you can actually do the processing itself, right? So you notice there's quite a bit of significant overhead if you have to do a PIM to PIM architecture. So again, this is the same, on the left is the same plot that I've shown you earlier. If you look at the overall speed up, just not the compute speed up, what you'll notice is obviously the performance starts to get worse, right? Again, this is why, because of the communication, which is shown here on the right. The next plot is a lot more interesting. This is where the overall speed up actually starts to degrade because of the significant amount of communication that's required. Right. So for this particular example, actually we needed to do some form of reduction between the data that were gathered, and because of the amount of data that you actually have to collect at the host itself, you'll notice that for 1,000 DPUs or 1,000 cores here, the amount of compute was actually a small fraction, and the majority of the time was actually spent on the communication itself. So again, to address this, I think we need both a architecture and a software solution. So this is what we proposed as part of this work, but which was a domain-specific interconnect. Again, I come from an interconnection network background, so what I try to do is, can we implement something that's specific for this PIM architecture? Something simple enough that could be done within a PIM DRAM constraint, yet expand the locality that was a problem. Now again, we're not the first to actually put it in wires. So the picture on the left is a block diagram of a Hynix PIM architecture, and you'll also notice this red lines that I've highlighted here, which is what effectively connects the central buffers to all the local buffers as well. So it's effectively a simple broadcast buffer. What we're sort of proposing as part of this work was make that into a network where you allow communication between the various different PIM nodes. Given the time constraint, I'm not going to go into the details. The details of this was published in an HPCA paper earlier this year. Now, again, given the interest in perhaps some of the folks here, I'm going to sort of highlight what changes it meant for the software. So if you were to execute 2 kernels with communication in between, this is what it would require you. You actually do the computation, you send the data to the host, you perform the communication, and then you send the data back, and then you launch the next kernel here and execute. So what we're proposing here is that, well, instead of doing this sort of fashion, you do all these sort of pre-processing here, and you combine this into a single kernel, where you offload the kernel as well as the actual communication itself, and then the kernel, the follow-on kernel as well, to the DPU, such that you don't have to go through the host. Right? So again, it allows you to have this sort of direct communication between the two. And again, this has to obviously be supported both by the hardware as well as the software. So again, I don't think this is a simple problem to solve. Again, it needs both sort of the support from both the hardware and the software, but also faces significant constraint, both from a hardware packaging perspective, as well as from a software perspective. Again, you want to make sure you have minimal impact on the actual interface itself, but obviously want to make it programmable as well. So when we did this, we were sort of trying to use the NVIDIA GPU model in terms of collective communication as sort of a starting point where you're sort of offloading the kernel to the processing core as well. Now, let me switch gears and talk a little bit about, given the domain-specific architectures, what does it mean for memory management? So there's two work that we've done the past couple of years where we looked at memory management for both a domain-specific architecture as well as domain-specific memory or PIM architecture. So one of the works we did, this was several years ago, where we actually proposed MMU for a NPU type of an architecture. Now, if you read through the papers, all the key observations is not surprising to anyone that has studied memory management in any sort of way. But I think the key aspect here is that it hasn't been done for an NPU type of an architecture. And obviously, you want to sort of exploit the various different characteristics of the workloads that we were targeting back then. So again, just sort of plopping down a whole bunch of page table walkers was not going to be the most cost-efficient solution. So it goes through various different ways of how we can sort of keep better track of outstanding requests without having to put a whole bunch of page table walkers. So again, the key insight here is the fact that, again, if you have different architectures, the current assumption is that, well, you don't need a memory management unit. And again, in some cases, you probably don't. But in other cases, you should start thinking about introducing memory management units. Now, the second aspect is this work that was done in collaboration with other folks, including Hynix here, is how memory is managed in the PIM architecture. So again, PIM is great. It allows you to put compute near the memory. But the key thing is the memory itself is very limited. You're talking about a few gigabytes at most, right? If you're trying to run any sort of a reasonable workload, you're going to need a lot more memory capacity than that, which means you can't get away with a single PIM device, right? So the fact is, well, how do you integrate all that? Well, you have to scale out. So here I'm going to take a picture out of what Hynix presented a few years ago, where they actually scale out the PIM system in a hierarchical manner. Right, you have individual ALUs in banks across various different chips and across various different nodes to be able to provide the amount of memory capacity needed, as well as obviously the memory bandwidth and the compute throughput as well. Now, having said that, I think the key observation or the key interesting aspect that we've looked at for PIM here is how do we manage the memory itself? So again, the key difference of this particular work was that we were looking at LLM inference in terms of long context. And again, the challenge here is that you have diverse set of input context lengths. And a lot of prior work, we're assuming you're running in one particular load, you have a fixed amount of memory you're going to allocate, boom, you're done. But obviously, that's not going to be the case, right? Again, dynamic memory management is something you learn in your introductory computer architecture classes. But what we're trying to sort of identify here is that this also needs to be done for a PIM sort of an architecture. Now, the interesting aspect here is that once we sort of fix all the memory management aspect, the interesting thing that was learned from this particular work is that the I/O all of a sudden becomes a bottleneck, right? It's not the internal DRAM where it's the compute, but it's the I/O that actually becomes the bottleneck as well. So those are some of the things that you need to consider when you especially have good memory management. Now, again, I've talked a lot about technology, and I thought I would wrap up this talk with talking about some of the technologies I think maybe will be considered, you might see in the very near future that will definitely affect how we think about memory or memory management. Again, you've talked about sort of, I would say, general purpose memory. You have your LPDDR, GDDR, HBM, and then you have PIM sort of memory on the extreme case, the various aspects that I've talked about before. But now you have sort of something interesting in the middle where people are talking about this notion of a customized HBM. Again, it was sort of hard to find any sort of picture related to this, so this is some of the pics that I could grab from Marvell's website here. But the current HBMs have a memory stacked on top of a logic layer. The logic layer was, for the most part, handled with memory processing technology, which means it did not give you the opportunity to put a whole lot of transistors. Starting with HBM4, they're actually moving the logic layer technology to a logic technology, which means you can put a whole bunch of other logics on top of that. And the key difference is that the IOs are no longer restricted to DDR, right? So again, the tiny circle here on the bottom sort of highlights what could change with this new customized HBM. But the other thing is there's two other things that needs to be noted here is now you have a whole bunch of area, silicon area, to put compute if you wanted to. But if you look at now all the other aspects of the HBM chip itself, it allows you to have more IOs added to the memory, which means you could connect up the HBM to other chips, whatever that might be. Again, that could be more HBMs hanging in a sort of a daisy chain, or it could be sort of other memory technologies added on top. So again, the key thing here is that this is perhaps, again, this is not a far-fetched technology. This is something that you might see in the very near future, and it's just something that we as a community should be worrying about in terms of how we treat this, both from a memory hierarchy perspective and memory management perspective as well. The second part here is sort of, I think everyone has sort of seen this, and I guess I'm sort of biased because I'm starting my sabbatical at Tens Torrent, and they're really big on chiplets. So I'm just going to talk a little bit about chiplets. Again, I think all of you have heard of this notion of chiplets. It allows you to integrate various different aspects, and it makes a whole lot of sense from a business technology perspective. But again, at the end of the day, it's sort of all about how do you manage all that resources, the components. How do you integrate them together, and how is the entire system viewed? Now, it's going to be pretty clear whatever systems you build out of a chiplet, it's going to be heterogeneous, right? You're not going to have uniform die chiplets across. You're going to have different types of chiplets. You're going to have memory chiplets. You're going to have different memory technologies. And on top of that, my favorite part is obviously the network. How are you going to connect all these together? And how is that actually viewed by the programmer or from the system's perspective? So again, I think those are some of the new technologies I think people will have to worry about in the very near future. So let me try to summarize what I've talked about. Again, this summary is just a list of various different questions I thought people should be thinking about. I think the basis of computer architecture has been Moore's Law, which is all about technology. Now, technology has and will continue to evolve. I don't think that will stop evolving. And memory technology will continue to evolve in one way or another. Again, whether it's sort of a CXL memory or a PIM sort of a structure, or it's different type of 3D stacking. The question is, well, how is that going to be integrated, or how is that going to be integrated to the compute part? Again, wherever that compute might lie. And obviously the question will be, how do you manage the memory? I think for many, at least for the students, some people often look for just new problems. Sometimes it's the same problem in a different setting, and I don't think that's really a bad thing, because the same solutions that apply to a previous problem might not be applicable. So those are some of the things to think about, and I think one can argue that memory, both in terms of capacity and bandwidth, will continue to be a bottleneck. So again, is the commodity way of DRAM. I think for the past 20, 30 years, DRAM has been viewed as sort of a commodity. Will that still be the case? Again, there's obviously the benefits of economy and so forth, but will memory itself become domain specific? Now again, I started off this talk with a eulogy for a memory vendor company, but processing in memory or near data processing or in different forms of compute near memory remains, I think, an attractive alternative. How it gets integrated, how it gets adopted by the community or the industry, obviously still remains to be seen, but obviously does provide significant benefits. Again, I haven't talked about all the benefits, but in terms of bandwidth, not only the memory bandwidth, but in terms of power savings and so forth. So with that, thank you, and I would be glad to take any questions.
So when you mentioned your work, Janus, so the problem was that there's a lot of shared data between MPU's memory space and PIM's memory space. But what if we consider batched inference? So if we consider batched inference, then often case most linear layers become matrix multiplication. So the only gem matrix vector multiplication will be attention head. So in those cases, I think only KV cache need to be stored in PIM's memory space. So it doesn't seem to have a lot of shared data between them. So is it like out of scope for Janus?
No, I think that's a very valid question. But I think you're giving me one example. I think there's a lot more example where the balance between the NPU usage and the PIM usage will vary, right? Some work will be dominated by the NPU usage. Some might be dominated by the memory PIM usage, and some might be sort of mixed half and half, right? So I think it's really important that you sort of be able to adapt to the different types of workloads, right? And again, even if you don't have any sharing, you still have the added benefit of memory capacity. So it gives you the benefit of being able to run bigger models as well. So I think there's definitely benefits to that. Again, what is the right balance? Again, one thing I didn't talk about is there's a balance in terms of how much compute you put in the PIM, right? You could put in one compute unit for one memory bank, or you could put in one for two memory banks, right? And obviously there's various different trade-offs along those lines as well. So again, I think that's a very valid question. It will depend upon the workloads, but again, I think that's why I would argue you need to unify the PIM with the main memory as well.
Thanks for the great talk. One of the things I was thinking of as you walk through that is the question of distribution in the network that you talked about, so the PIMs can communicate, and the different application domains where someone might use this. And one application domain that's probably dear to quite a few people in this room is something like garbage collection, where you're doing a graph walk, graph traversal, you're doing pointer chasing, and you don't have that locality you might get with a matrix multiply or something like that, where you can just do a transpose and put it into the different PIM banks or whatever, memory banks or whatever it is. Instead, you've got to follow pointers, so you've got this locality thing. So that seems like a very different application. Well, it seems natural in the sense it's memory bound because you're doing a graph traversal, but it seems difficult in the sense that you've got this this problem with the distribution of the memory. So I just wondered if you had any super high level thoughts on the application domains that are going to be working with this and those that aren't, with respect to things like locality.
That's actually a great question, and I asked a similar question to my students, so I wasn't able to get a great answer, but I'll try to provide you with my thoughts. The work that we did, we sort of cheated in the sense that the communication was very structured, regular, right? So it was sort of like a collective all-reduced sort of operation where you know exactly what's going on. So what we meant was we were able to design the network to accommodate that. It was not a general purpose network. Now, if you have something very random, you would actually have to provide a network that supports our random accesses. And I would argue that might be too costly to supply in the PIM architectures. But hierarchy, I think, is our best friend here. You don't need at every level of interconnect to provide the full connectivity. I think if you provide, let's say, a chip-to-chip connectivity through, let's say, a buffer chip, again, it's maybe not as, provides you as much locality if you had sort of bank-to-bank, but I think it's a nice compromise. So I think these type of workloads are exactly why I think you need some amount of communication within them. But having said that, the biggest challenge I would argue is that now the host does not see you as a memory, because now the latency, everything is non-deterministic. Again, the work that we did, we assumed PIM was working in sort of a deterministic manner because the communication itself was deterministic. But if you have a random access, I think it's an interesting thing to explore. It definitely would improve the benefit of PIM itself, but then you also have to worry about this. Do you want to have a full-blown general purpose network or not, or something in between? How is the host going to be able to manage that, given that it's going to be random access as well?
Questions. Thanks again for a very interesting talk. There's something I was wondering when you were talking about the distinction between seeing PIM as an accelerator or memory. Something that's come up in workloads I've seen in the last few years has been an innovation in terms of the storage formats for floating point in HBM. So things like the MSFP block formats, where you have a shared exponent between a bunch of mantisas that are then stored. And that can be challenging to program with GPUs, because you have to load the data and convert it from that block format to what the GPU is wanting to be processing, and figure out how to do that in the maybe the different block sizes that the tensor core is designed to handle. I was wondering how you'd see that kind of data type conversion fitting in here, whether some kind of on-the-fly conversion that would let people innovate in the storage formats would be something that current PIM systems support, or maybe an interesting direction in the future.
I think it's a very interesting question. I don't have a good answer, but I think some of the things that you can think about. For example, one of the Hynix PIM, I believe, just supports a single format, right? So obviously that does not give you the flexibility. If you did something with something similar with an UMM type of PIM, you could do whatever you want, because again, you have a general purpose core. It could do even floating point operations and so forth, but it would emulate everything effectively. So the performance would obviously drop significantly. To be honest, I think it would sort of have to come down to sort of a balance of, in terms of memory bandwidth, memory capacity, compute in terms of what needs to be done, as well as the communication overhead. So again, what is that right balance? And does that make sense to introduce that to save on the capacity versus the compute overhead? So again, I think it comes down to how you're going to design the entire system. So again, whether you view it as an accelerator memory, it's only one part of the system. Right. I think you have to look at the system as a whole to be able to come up with a great answer for your question.